Hey guys, welcome back to another episode of the Genesis Block podcast. For the newcomers here, we are Genesis Block. We analyze crypto protocols and crypto themes. And just to give you a flavor, the crypto themes that we've analyzed so far include, Web3 music, creator economy, MEV, so the whole array. And on the protocol side, we've analyzed protocols such as Frax, Audius, and once again, as you can guess, it's the whole array from DeFi to NFTs to the consumer stuff, everything. And we do this by posting articles and podcasts such as this. Today, we have Siddharth presenting to us zero knowledge proofs. And yes, we know that this is an incredibly complicated topic. So he's gonna try to, simplify it as much as possible for us. So, the the more the newbies of the technical space, such as myself, can understand hopefully something. But with that, Siddharth, why don't you take it away?
Perfect. Thanks, Sid. And yeah, today we're going to talk about one of the most interesting topics in the Web3 space, according to me, which is zero knowledge proofs, but also for, most people who are not the biggest fan of, math and mathematical algorithms, cryptography, things like that. This topic may seem very daunting at first, but don't really worry. We're not really going to get into like the deep mathematical algorithms that power zero knowledge proofs and at the heart of the cryptography that define it, but we're actually going to understand practically how zero knowledge proofs work. So using a few examples to illustrate this and bring this to life a little bit more. And rather than going into the cryptographic techniques and anything too complex, we're actually going to talk about two types of applications of zero knowledge proofs. So one of them we'll touch upon the practical applications of zero knowledge proofs within the world that we live in today. And the second part of it would be how zero knowledge proofs are actually being used to scale and improve blockchains and blockchain networks in general. So they have wide applications at the core of blockchain technology that can improve data privacy, that can improve, proofs that something has actually happened, as someone has said it's happened without compromising on any privacy. And that's one of the most exciting applications or that is the most exciting application of zero knowledge proofs. And we're going to dive deep into it today. So before we get started, I think that we need to align on terminology and a few different aspects of zero knowledge proofs, so that we can actually get into the meat of this episode without you just shaking your head and saying, "Why am I listening to this? What am I actually doing on this podcast today?" We're actually going to try and explain some of these terms in as easy a manner as possible, while also appreciating the extremely complex and technical nature of zero knowledge proofs and the essentially the moon math that makes up zero knowledge proofs. But we promise that this will be a very interesting journey. So to get into the glossary at first, before we actually dive into the world of zero knowledge proofs, first we actually need to understand what a zero knowledge proof itself is. So what zero knowledge proofs do is that they let someone prove that they know, have, or are something without giving up any information about what they know, have, or are. So at their core, zero knowledge proofs are essentially allowing me to prove that, let's say, I'm my age without actually telling the person I'm proving my age to my actual age. So that means this preserves my privacy while allowing the other person, the counterparty, proof and verifiable proof that I am who I say I am without a shadow of a doubt. And the reason that the second part of that, without a shadow of a doubt, is so important and the way that it comes to be is that zero knowledge proofs have strong cryptographic guarantees. So, what that means is that you can cryptographically, mathematically be certain that what I am saying is correct to a very, very high degree of probability. And that is because they use cryptographic techniques that you don't really need to understand what they specifically are, but they include things like digital signatures, hashing, or elliptic curve cryptography. And these techniques provide assurances that the underlying data has not been accessed, modified, or disclosed in any unauthorized manner. So these guarantees are achieved via mathematical algorithms that make it practically impossible for attackers to break the encryption or tamper with the data. The second thing to understand is the two types of zero knowledge proofs that there are. Now, we don't need to delve too deeply into either of these during the episode as well, but it's important to understand that there are two types. So there's ZK snarks and ZK starks. Now, you don't need to, again, at this stage, go into what exactly the full form of a snark is or a stark is, but essentially, what you need to know is that zero knowledge ZK snarks rely on this method called trusted setups, which we'll get to later on in the episode. And they're faster and less computationally intensive than ZK starks, but they're also less secure. So as with blockchains and in every area of this field, there are trade-offs associated with every decision that you make. So if you choose a zero knowledge ZK snark, you will choose a type of proof, a type of zero knowledge proof that is much faster to generate, but is also less secure than a ZK stark. So that's the important thing to level set on. And the third piece of terminology to understand is a ZK EVM. So let's break that down in two parts. So what is an EVM? An EVM is the Ethereum virtual machine. So it's a virtual computer that executes smart contracts on the Ethereum blockchain. So essentially, you write a program and then you execute it via the Ethereum virtual machine. And this is at the heart of the Ethereum ecosystem. It's what connects all of the different blockchains that build using the Ethereum virtual machine. So a ZK EVM is a privacy-focused version of the Ethereum virtual machine, and it enables smart contracts to be executed without revealing the inputs or outputs to anyone except for the parties involved in the transaction. So the only person who know the inputs are the person doing the input, not even the person who can see the output. And the only person who knows the output is the person checking for that output. So there's privacy on both sides of the equation. And the beautiful thing about this is that the privacy is enabled with the strong cryptographic guarantees, like I mentioned earlier. It essentially means that there is privacy, but it's verifiable privacy, that you know that what is being proved is correct. So ZK VMs use zero knowledge proofs to validate transactions without revealing any sensitive information, which allows for private and secure transactions with Ethereum. And obviously, the biggest benefit of ZK VMs is that they're EVM equivalent. So what that means is that existing apps on Ethereum can be migrated to systems that are built on ZK EVMs, like layer 2 solutions like ZK Sync or Polygon ZK EVM or Scroll, which have released their mainnet solutions or are releasing them very shortly. So because they can be migrated with little to no rework, this significantly reduces development efforts, and it also makes it much easier to deploy apps that are already on Ethereum to those ZK AVM solutions. So it allows those solutions to actually become those blockchain solutions using ZK AVMs to grow much more quickly than other types of solutions that are not EVM equivalent. So now,
I've got a question here.
yeah, let's go.
A quick question on the ZK EVM bit specifically. Is the ZK EVM an alternative to the regular EVM from a developer's perspective, or do developers use both in conjunction when they're making an app? So, for example, if they want to release an app which has some zero knowledge properties, they run the ZK EVM, but then for the rest of the decentralized application, they run the EVM. Or so how is the interplay between the two?
So essentially, the ZK AVM it would be on a particular layer 2 solution, right? So we'll give you a primer, a refresh on what a layer 2 solution is. It's a layer 2 solution is essentially a roll up, or it's essentially a way to scale Ethereum. It's like a blockchain built on top of Ethereum or another blockchain, but usually Ethereum. And it essentially aggregates transactions that happen on the layer 2 solution, and it posts them back onto Ethereum for validation. Now, there are two types of layer 2 solutions. There's optimistic rollups and there's ZK rollups. Optimistic rollups essentially there's no need to get into exactly what those are for the purposes of this episode, but a ZK rollup, essentially what it does is it aggregates transactions that happen on the ZK rollup, and then it publishes a zero knowledge proof that those transactions happen to the Ethereum mainnet, right? And the validators on the Ethereum mainnet validate that this proof is actually that this proof is actually correct. Now, to your question, when a developer is building on a ZK EVM on a layer two solution, they don't actually need to build on the EVM solution itself because you're building a dApp that is specifically for that blockchain solution. So what a ZK EVM does is it actually gives developers the comfort and the known surroundings that they have of developing on the EVM. It's essentially meant to be a way for developers to be able to develop on layer two solutions as
Got it.
easily as they can develop on layer one solutions. So you don't really need to re-execute your transactions on the EVM. What you need to do is that when a proof is sent to the Ethereum mainnet, that proof is just validated by the validators, and you don't really need to re-execute any transactions or rerun any applications. That's it.
Understood. No, that makes sense. So essentially, it is the virtual machine of choice for developers who are developing on the ZK rollups or the
Yeah,
blockchains that that effectively utilize the ZK proofs on top of whichever base of the blockchain.
exactly. And
Got
and
it.
the way to think about it is, and like obviously there's more nuance to it, but like if an application is only on Ethereum today, what the developer can do is essentially just copy paste the code that they have for that application on Ethereum and paste it on the layer two solution, the ZK rollup, and they can then deploy that application without many or any modifications to the layer two solution.
Mm,
So therefore, it makes development effort. It significantly reduces development effort to deploy that application on a layer two solution.
perfect. Makes sense.
Cool. So yeah, let's just like dive into, zero knowledge proofs. So let's just illustrate how zero knowledge proofs work first with an example. So, picture this, you're standing outside a club, waiting to get in, and the bouncer stops you at the door, and he wants to check your ID. So you give him your ID, and he sees, so along with the one fact that he's actually looking for, which is that you're above 21, he sees all the other information about you, which he doesn't need to know. He sees your name, he sees your address, your visa status, national insurance number, whatever it is, right? And he doesn't need to know any of that. And it's just like leaking your data to him without him needing to know it. So what if instead he could just scan a QR code on your phone that would prove the one fact needed to enter the club, that you're over 21. That's it. And completely verifiably prove that you are over 21. He would get access to no other information about you. Now, this preserves your privacy, and this is what zero knowledge proofs enable. So the first time zero knowledge proofs and blockchains interacted with each other was way back when, actually. And it was in Zcash, where zero knowledge proofs enabled the network of computers that were running the Zcash protocol to verify that every transaction is valid. So while maintaining the privacy of the transaction data. So exactly, like what has been said about the zero knowledge, the ZK rollups, etc. But the problem with Zcash is that it didn't actually scale very well because it used ZK snarks that then and until very recently were computationally intensive, and they made transactions slower and more resource intensive. So that means that what that does is two things. It means that the amount of time for a transaction to settle is long because it actually takes time to generate a proof that the transaction has happened. They were also computationally intensive, so that meant that they weren't exactly environmentally friendly. And also another thing was that because they had such high computation requirements, that anyone with a laptop or a phone could not actually generate proofs. You needed to have a certain degree of hardware to actually be able to generate these proofs. So that means that it very much centralized the proof generation process and therefore centralized the blockchain itself to an extent. So that was an ideal. So and another thing was that with Zcash, it's especially the team prioritized privacy over scalability, which is fair enough because that was what the network was meant to be about. It was meant to be private transactions of money. But they this is at the expense of some speed and scalability. But now the tide is turning, right? So ZKPs have been gaining more and more attention over the last few years because the technology to create them is advanced enough to reach production scale. So, like for starters, the layer two solutions that we've been talking about, the race to deploy and be a first mover in that to deploy a ZK AVM solution was very hot. and it's only just culminated in Polygon and ZK Sync actually releasing the mainnet solutions of their ZK AVMs. So and there are other teams building, right? There's Scroll, there's Consensus, there's EKVMs are not too far behind, and all of them have built similar, but similar GKVMs that differ in like a few different areas according to trade-offs. Again, don't need to get into that at the moment. And what's also good is that the ecosystem is actually understanding now and coming to a point where everyone's recognizing the fundamental benefit of zero knowledge technology for many different applications. And what the main benefit actually is to preserve total privacy and confidentiality while simultaneously verifying the truthfulness of a statement with a high degree of certainty. So what that essentially means is that you can apply zero knowledge proofs in many different applications. You can apply them in digital identity, like the example of the bouncer. You can apply them for ratings and risk assessments for financial instruments, private, making sure that the compliance process, so KYC, KYB, or AML, all of that stuff is actually private. Proof of ownership or activity, digital voting, so many different ones, right? So obviously, like as you can see, these are many commercial applications, and therefore they're likely to gain interest from an institutional perspective. So yeah, and there are, as we'll explore later on in the episode, there are many projects involved in the ZK ecosystem that are building solutions that are scaling and improving the technology itself, and also using the improvement in ZK technology to scale and grow blockchains at the base layer, right? So let's now go over how exactly zero knowledge proofs work.
So,
Then,
Siddharth, one
yeah,
thing just
sure.
before you begin on the explanation, I just want to preface it um, by saying that what we're talking about sounds like magic, honestly.
Yeah,
We're saying that you can prove something without having to reveal the information, or just essentially take your word for it. Obviously through computation and mathematics or whatnot. So it does sound like magic, but one thing I just want to remind the viewer or the listener that all technology at one point was like magic. Electricity was magic. The mobile phone was magic. The internet was magic. And if you really describe those technologies just using just simple words, it does still sound like magic. So just keep that in mind before just ignoring what we're talking about and just dismissing it as just all more things that
fluff.
just work in theory but not in practicality. So
Yeah.
yeah, with that,
So
Siddharth, why don't you take it away again?
yeah, no, just to add to that, right? Like Arthur C. Clarke had one of the best phrases, in my opinion, which is any sufficiently advanced technology is indistinguishable from magic.
Yeah.
And that's there's a phenomenon where you're kind of going back in time and picking up someone and taking them back in our time, and the question is how far behind would you have to go to like make someone faint of like shock, right? That,
Mhm.
oh, they've come into this like insanely advanced world where there's just magic. And like now, with the pace of technology growth, the technological growth and evolution, even if you
Mhm.
took someone from like 1910, 1920, even then I
Yeah.
can't really predict the time, but that would be the case. And
Yeah.
in 1910, I think the case actually for that would have been something like 1700, 1600 something. So like the essentially what the point is that the pace of growth of technology is
Yeah.
um crazy, insane. And all of this stuff might sound crazy, but there are actual practical applications being developed for with it. And for the most of us, I think that there is a bit of a point where you have to understand that, okay, you're not going to be able to probe each assumption down to like the nth degree, where and for zero knowledge proofs to do that, you would have to be one of those moon math professors. So at this point, I think that we're taking some of these assumptions at face value and saying that, okay, if you cannot break it, you can't break it. And that's what we're doing in this case. But it's not to say that it's not the right thing to think about, like, oh, this is the assumption, this is the base layer assumption, this is the base layer assumption, and going down and down and down that rabbit hole. And that's the correct way to think about everything. But yeah, in this case, to actually understand what is at the base and the core of like zero knowledge proofs, and you would have to understand the mathematical algorithms that make zero knowledge proofs up, and that's going to be a difficult task for most of us. So at this point, to understand the potential of this technology, we have to take some of these assumptions at face value. Cool.
Absolutely.
So let's go through how zero knowledge proofs actually work. So firstly, there are two key actors in the creation of a zero knowledge proof. There's a prover and a verifier. The prover convinces the verifier that they know a certain piece of information without revealing that information. So let's explore this through an example. So let's say Alice wants to prove to Bob that she knows the password to a locked box without actually revealing the password to him. So what Alice does is she puts the locked box in a room and leaves. Bob then goes into the room, opens the box, and retrieves a piece of paper with a random string of characters written on it. He then locks the box again and leaves the room. Now, Alice then comes back into the room, and Bob asks her to prove that she knows the string of characters on the paper. Alice then performs some computations on the string of characters. So basically, like she, does like some computations being like addition, subtraction, essentially mathematical things to prove that, she knows the string without actually revealing that string itself. So let's say there's like a string of random numbers, and then you go like, okay, if you multiply this by X, then you get that answer. It's divided by this. That's a very rudimentary way of understanding the computations. But she essentially does some computations that says that, okay, I know this string. Without actually telling Bob that what exactly that string is, right? So Bob is then satisfied that Alice knows the password, even though he never learns the password himself. So what happens is that because Alice proves that she knows the contents of what was the exact contents of what was inside that box, she proves to Bob that she has opened that box, and she knows what is inside that box, so therefore she knows the password to open that box, right? So it's a way of saying that, okay, I because I know item B, you can be very sure that I know item A, because I cannot get to item B without knowing item A, right? Sid, I'll stop here actually to see if you understood that was clear.
Yeah, no, I think it makes perfect sense. Essentially, if I had to summarize your there are two events that are related to one another, and let's say event A and event B, like you mentioned. And the only way to know event B is if you know event A. And what you're doing via ZK proof is proving that you know event B. And as a derivative, then it's deductible that you know event A.
Exactly.
So that's how I understand it. I think what you said makes perfect sense.
Okay, exactly. Cool. Perfect. That's one tough job done. So Alice is the prover and Bob is the verifier. And what this does is that it ensures that Bob can be convinced of Alice's knowledge without revealing the information to him. So Alice then creates this proof and hands it to Bob to verify its accuracy. The computation is the proof, and then Bob verifies that the computations are correct. So what happened initially when zero knowledge proofs were created is that they were interactive. So to prove something, you must play a game with a verifier. So think of it as a lie detector test, right? So where one party asks questions and the other answers until the truth has been established. Now, more and more ZK proofs are actually non-interactive. So what actually happens is that you can generate a piece of data that acts as a proof that can be directly submitted for verification without needing any of this back and forth communication. So this increases speed and scalability. And another key aspect of zero knowledge proofs is what I've called configurable privacy. So what that means is that it allows you to selectively hide some or all inputs. So if you wanted, you could actually reveal some of the inputs that you've put in, or some of the outputs, right? But you don't need to do that. And that means that your privacy, the level of privacy in a system, is configurable. And that has many applications, because institutions, individuals all have differing levels of privacy requirements. And therefore, having configurable privacy actually boosts their systems and boosts the use cases available to them significantly. And now, what has actually started happening with the development of the technology as well is that to improve the integrity and scalability of zero knowledge proofs, third-party providers can also generate these things called proofs of computational integrity, which guarantee the output that is being received. So you can add a further layer of security on top of it. Cool. So, Sid, all clear on zero knowledge proofs and how they
Yeah,
work?
as much as it can be. Yes.
Perfect. So now let's just dive into some applications, right? So some examples of how zero knowledge proofs can be integrated into everyday tools. So firstly, it's like the identity example, right? Which is what I said around the bouncer. But an institutional and retail use case that's interesting is cloud computing. So institutions and individuals can use cloud computing without sharing any private and sensitive data. So for example, I can prove my identity to a cloud service provider without revealing my credentials. So without revealing like my password or anything like that. Or an institution can verify computations that are done on private data stored in the cloud without actually exposing any private data. So what you can do is understand the components of that private data, exactly like what you can get what you want out of that data without actually knowing what that data is, right? These are big unlocks for individuals and institutions.
So,
Another one is access control. Okay, go on, sorry.
I just wanted to give another example of the data point that you made. A more relatable one, right, is social media advertising. Right now, what happens is, that you have your social media users. So let's take Instagram as an example. You have the Instagram users, you have Instagram itself, and then you have advertisers. What happens is advertisers go on Instagram's, advertisement portal, and then they say we want to, advertise to XYZ criteria of user, and then they pay Instagram to serve those ads. But the thing is, while Instagram does not, directly reveal these data points of individual users to the advertiser, we're still trusting Instagram to, keep those records safely and not be exploited and such. And through the, events such as Cambridge Analytica and whatnot, we know that that's not a good enough guarantee. So if we employ ZK proofs to the system, essentially what we're doing is we're doing the exact same stakeholders, except we're eliminating Instagram or the social media website to even accessing our specific data. They know, it's us account A and account XYZ that has this data, but they don't actually know our name. They don't know, the exact specifics. They just match make the advertiser and the ad without even them being able to, be able to sell the data to a third party, which happened in multiple situations. So that's just a more
Cool.
relatable example.
Yeah, that makes sense. Perfect. Yeah, so I'll just quickly run through some other applications practically about how zero knowledge proofs can work in the world that we're in today. So for example, you can use them to prove that a person has access to a certain resource without revealing any information about the resource or the credentials used to access it, right? You can have copyright protection. So you can prove that a person owns a piece of content without revealing the content itself. Now, where is that going to be useful? It's going to be useful everywhere there's, an image generating AI tool like Midjourney. So for example, an artist can actually, potentially prove using zero knowledge proofs that they are the ones who initially created that content, which is a huge thing. And I think that, this is a very interesting avenue to explore further on, to actually give power back to artists and creators, of the content that they have created and that's being used in many different manners today. Credit scores. So individuals and institutions can prove that they've got a good credit score without revealing their actual credit score or any other personal financial information. And another one is investment portfolios. So zero knowledge proofs can verify the accuracy of risk assessment data without revealing any sensitive information about the investments themselves. So, this is very important in scenarios where, let's say that, you've got institutions where multiple parties need to collaborate on risk assessments without actually exposing their investments to each other. It's huge because then you won't actually be able to see the investments that the other party has made, but you know that they are, well, how risky they are, whether they're not, etc., etc. Um, cool. So, and in terms of blockchain specific examples, right? Like what we've talked about already. So layer two solutions. So where, when a when a ZK roll up is published onto the Ethereum mainnet layer one, it includes a proof that all the activity on the layer two was legitimate, along with a complete list of all the changes to account balances on the layer 2 since the last proof of transactions was posted. So, it helps scale blockchains quite a lot. And what layer twos also do is that they increase transaction throughput by processing transactions off chain. So when you process these transactions off chain, there's obviously a bit of a security risk, and you don't know whether those transactions were processed correctly. And what they do is that they actually use zero knowledge proofs to verify that those transactions were conducted accurately and legitimately off chain, which is a big unlock, and it actually ties the off-chain and on-chain worlds a lot more closely together. And yeah, so this increases speed quite a lot and helps in decentralizing the network as well. And another use case is privacy-enabled stablecoins. So let's say that a stablecoin is created where the issuer can verify the compliance status of all holders, and they can maintain a complete audit trail. And they're also preserving the privacy of holders from both the issuer and the rest of the world. So these are some blockchain related applications where zero knowledge proofs can be incorporated. Sid, any questions there?
Oh, we're good. We can continue.
Cool. Perfect. So now I think that there's before diving into some of the applications of zero knowledge proofs and how blockchains are using them, and before understanding what is being done to scale and improve the technology itself, we need to understand what are some challenges with ZKPs, right? Like with zero knowledge proofs. So firstly, they're slow and expensive. Since a large number of expensive math operations are required to generate a proof, so you're doing pretty complex math, it takes time to actually do that math and run it on a computer. Now, proving a computation first requires translating it from a classical program to a ZK friendly format. So you can't, just put like some Java code and go like, okay, like a prover is going to use regular code to actually be able to verify the proof. You actually have to create it into a format that is able to be digested by the prover, and the prover can therefore prove the validity of that proof, essentially. That proof quite a lot. But what that means is that more complex operations result in longer proof generation times, and some operations might not be friendly from a ZK perspective, right? This leads to longer proof generation times as well. Another problem, well, not really a problem, but another challenge is that an interactive zero knowledge proof, which is the first type of zero knowledge proof that we spoke about, requires this thing called a trusted setup. Now, in a trusted setup, what happens is that each member of a group of trusted parties generates a portion of a parameter, right? So the group, so the group as a whole essentially generates parameters. So let's just say that a parameter is like part of a key, right? A parameter is a total key. Each part of that group generates each member of the group generates a portion of the parameter or a part of the key and obfuscates it. The portions are then combined to create the final key, right? So let's say that I have the two of us, Yash, other people. Let's say there are two more people who are part of this trusted setup. What I do is I create a portion of the key and I obfuscate it, and then I pass it along to you. You then create a portion of the key, add it to my portion, obfuscate the entire thing, and pass it to Yash. Yash does the same, rinse and repeat for 5 people in the group. What happens is that no single member of the group can individually determine the final key, right? The problem with this setup, even though it's very secure, actually, is that it can be difficult to set up and coordinate this process. And it's secure if you've got the process and the structure done correctly. If you don't, then it can actually be not very secure, and introduce some security risks. And another thing is that like trusted setups actually require multiple rounds of verification between the prover and the verifier, which reduces the speed and efficiency of proof generation. And another challenge is that integrating zero knowledge proofs with existing systems can be difficult because most systems haven't been designed with zero knowledge proofs in mind, right? So how do we actually go and improve this technology, and how do we make sure that it's applicable from at production scale? Well, one of the things that people are working on is this is called hardware acceleration. So hardware acceleration, it refers to the use of specialized hardware to perform certain operations required for generating and verifying zero knowledge proofs. So the mathematical operations that are needed to generate these zero knowledge proofs, they can be sped up by using these dedicated hardwares, right? These hardware tools. So some of these tools are things that you might have heard of, right? It's like GPUs, graphical processing units, or application-specific integrated circuits, or ASICs, right? You must have heard of ASICs, which are used to, which are used for proof of work systems like Bitcoin as well. Another one, actually, that is a lot more specialized for zero knowledge proofs is called FPGAs. FPGAs are these things called field programmable gate arrays, right? And complex word, forget about it, call them FPGA. Now, and FPGA is the most promising of the three from GPUs and ASICs. And they're like small electronic chips that can be programmed to perform different tasks. Think of them like that. So they can be very flexible because they can be programmed to do many different things. So for example, you could program an FPGA to process, things like audio signals or to control the movements of a robot. So you can have very granular applications of FPGAs with which you can do things. And one of the biggest advantages of these FPGAs is that you can actually reprogram them or update what they actually do with new functionality if it's needed. So therefore, they're actually recyclable, they're reusable. And this makes them very useful for applications where you need to be able to change what the device does without having to completely redesign it from scratch. So this actually makes it easier to use. And this is therefore useful for ZKP generation if you have to change some parameters or do something where you need a lot more flexibility with the hardware that you've got. Um, and FPGAs are also preferable because the supply chain is pretty healthy and it's easier to buy them on the market than GPUs or ASICs, which are pretty much in demand for a host of other types of applications as well. So you can use FPGAs to speed up zero knowledge proof generation. And yeah, so in general, right? Another thing that hardware acceleration does is that they improve the security of zero knowledge proofs as well. So when you're using a device, what happens usually is that it leaks some information about itself, even though it's not needing to. So it leaks it by, for example, like how much power it's consuming or how much radiation it's emitting. And if someone is crazy enough to try and attack all of these devices, which many people are because they hold a lot of value, um, its power consumption or electromagnetic radiation can be tracked, which allows which allows for important sensitive information to be stolen, like cryptographic keys. So therefore, like FPGAs and other hardware acceleration devices actually stop some of these things from happening. So yeah, in general, these are some of the challenges with zero knowledge proofs and how they're being tackled. Um, Before I go on to the last part of this episode, which is to discuss some of the applications of zero knowledge proofs in blockchain technology today, Sid, is there anything that you wanted to discuss?
Yeah, I mean, just one point that, to make the point relatable of how ZK proofs are scaling, right? Especially the hardware. A good analogy is how, over the last few decades, computers have gotten smaller and faster, right, at the same time. And that was enabled largely to a very popular concept known as Moore's law, which basically said that, if I'm not mistaken, that every other year or so, the size of computer chips, they half, or something along those lines. Don't quote me on that. But essentially, the broad concept is the same, that, over time, the hardware is exponentially getting, that much more sophisticated, which allows the software implementation, such as knowledge proofs, to be that much more, efficient, faster, and secure at the same time. So that's a good analogy, for people to, understand how ZK proofs are improving over time.
Cool. Yeah, exactly. Yeah, that makes sense. Perfect. So now, let's talk about three projects that are using zero knowledge proofs at the core of their designs, or actually enabling zero knowledge proofs to improve blockchain applications. So the three projects that we'll touch upon today are Aleo, Lagrange, and Espresso Systems. So firstly, let's talk about Aleo. So Aleo is a blockchain that uses a Bitcoin-like architecture. So what it does, it's got a ledger, obviously. So it's got a distributed ledger, and the Bitcoin system is the UTXO model. So not really going to go over the UTXO model at the moment, because it's not really relevant for this, but it uses a UTXO model. So to understand Aleo and the cryptography that's at the heart of its design, let's step back a little bit and understand a little bit more about how Aleo was founded and its origins. So before any of these advances in generation of zero knowledge proofs, it actually used to take about 3 hours to generate a ZK snark proof. So this obviously limited the use cases it was applicable to, and reduced its applicability in terms of practical applicability, and it made it more like, oh, this is a cool academic theory rather than anything practically useful. But then there was a breakthrough. So the founder of Aleo, this guy called Howard Wu, he published a new, more scalable form of cryptography called DIZK, or I'm just going to call it DIZK. So DIZK, distributed zero knowledge proof generation across machines, right? So when you distribute this proof generation, so when many machines together can combine and generate one proof, it obviously significantly reduces the amount of time taken to generate a proof. So the more you can do something in parallel, that's one of the golden rules. The more you move something to be done in parallel, the quicker it will be to generate it, right? So its main innovation was that it was able to generate and verify proofs without a trusted setup. So moving from an interactive zero knowledge proof to actually a non-interactive zero knowledge proof. Now, what DISK did was it introduced a distributed element to the generation of zero knowledge proofs, right? So again, it also helped increase the decentralization of the and resiliency of the system. But the problem also was that it was still very computationally intensive and required a lot of communication between the distributed nodes in the system. So like node 1, node 2, node 3, all of them need to talk to each other to be able to generate the proof, right? So now the problem is that obviously this adds to the, well, it doesn't add to it, but it's still it is reminiscent of the same problem that zero knowledge proof generation had, which is that it's slow and computationally intensive. So DISK was a step in the right direction, but it wasn't the final product. And I don't really think that we're at the final product yet, but we're at a level that is today that is practically applicable. And what happened after DISK was that Howard helped create ZEXC. So I'm going to call that ZXC. So Howard created ZXC, which is an evolved form of DISK. It takes it a step further. So what it does is that it runs applications off chain and just verifies the proofs on chain, right? So transactions can be of many different sizes, and re-executing them on chain actually takes a lot of effort and time and cost. In the ZXC system, rather than re-executing the transactions that were done off chain or on chain, what it does is that it just checks the output and the proof, and this is much less computationally intensive, right? So this is how the system that we had before, which was doing everything on chain, essentially doing an interactive zero knowledge proof system, doesn't really work anymore. The way it actually works now is that all you need to do is check the proof that is produced off chain, like I mentioned earlier, right? So these were the innovations that allowed Howard and a bunch of other brilliant cryptographers to actually scale the system from being theoretically applicable and a nice academic a nice academic pursuit to actually a more practically applicable one. So what ZXC also did, which is really, really cool, is that it enables this thing called function privacy as well as data privacy. So what happens is that no detail about the transaction, even that it happened, is made public, right? All that you know is that a proof was there. There was a proof that was submitted and that was checked. That's it. You don't know what that proof was checking. You just know that something has happened on this blockchain, and essentially that the zero knowledge, essentially a zero knowledge proof has been submitted, and that proof has been checked. That's it. So that's a very important component. So what function privacy does is it protects the privacy of the inputs and outputs of a computation, making a transaction completely private. Now, this is, it brings to life a whole host of institutional use cases because institutions have many stringent and ever-changing privacy requirements. So what does Harvard do with this fantastic new form of cryptography? He applies it practically in creating Aleo. So Aleo, now to understand it, you need to understand that it's got two core components. It's got ZK Cloud and it's got the Aleo blockchain. Now, ZK Cloud is the off-chain computing component. So it's an off-chain computing environment where programs are executed privately, securely, and cheaply. And the Aleo blockchain, which stores the state of all programs that are built on Aleo. So like current balance, account balances, status of all transactions, and any smart contracts running on the network. So the way individuals interact with each other on ZK Cloud is via these thing called shielded transactions. So transactions are completely private. They completely hide the details of the interaction. So participants, amounts, smart contracts interacted with by using these thing called recursive zero knowledge proofs that are described in ZK. So recursive ZKPs, they used to prove to someone that you know a bunch of secrets. So I know secret 1, 2, 3, 4, 5 without actually revealing any of those secrets, right? So what you do is that you create a tree of small proofs. So let's say you've got like you've got a tree, and at the root of the tree there's like a bunch of different smaller proofs. So each branch of the tree, right, represents one secret. So one proof represents one secret, and all of these so what it does is it combines two pairs of proofs together. So proof 1 and 2, 3 and 4, 5 and 6, 7 and 8, and then it combines the and then what it does is it combines the pairs of the proof. So the proof that 1 and 2 and 3 and 4 were combined into proof A. Proof 5 and 6 and 7 and 8 were combined into proof B. So then it combines proof A and B into a bigger proof, and then so on and so forth. So what it does is it creates a tree of proofs, right? And then you just get to, obviously, at the top of the tree, you've got one big proof. Now that one big proof contains proofs that of all of the other secrets that are in that tree. So this big proof covers all the secrets. So it knows that all the secrets are legit while keeping them hidden. So in the case of Aleo, recursive ZKPs hide a lot of information. They hide the smart contracts interacted with, participant identities, and transaction amounts. Now, let's say there are all these shielded transactions happening on the ZK cloud that's off chain. These shielded transactions then link ZK cloud to the Aleo blockchain. So what happens is that you create on-chain, you create records to update the state of programs on Aleo, while nodes verify the proofs that are attached to the transactions, right? So these transactions each have proofs attached to them, and then these proofs are then verified by the nodes on the Aleo blockchain. So the nodes don't get to see the exact details of a transaction. They only verify that it's legit. And transaction throughput can increase significantly because nodes are only verifying proofs rather than running programs, which takes more time and more computing power. So yeah, now what's the difficult part about this is that obviously, some of these different transactions, and constructing these transactions and proofs requires cryptographic knowledge, and that's not easy for most developers also. So what they've done is they've created their own programming language called Leo, which is similar to JavaScript. And while this may make building on Aleo easier, one thing to note is that the need to learn a new language may somewhat slow developer onboarding onto Aleo. And what also happens is that you can outsource your proof generation to third-party proving services. So you allow proofs to be generated in parallel, like I said earlier, and you increase them the throughput even more. One last thing to know about Aleo is that when a block is added to the Aleo blockchain, provers are rewarded in Aleo credits for generating proofs. Validators stake Aleo credits to propose blocks made up of these proofs, propose the blocks to be added to the Aleo blockchain, and verifiers check whether the proofs within the blocks are correct. And they all receive Aleo credits as rewards. And now again, if you've heard this podcast before, you know that our main question always is, do you need this token? And while introducing Aleo credits helps decentralize and incentivize proof creation, is it necessary to have another native currency like Aleo credits, or could you have done the same thing with ETH, right? So that's an interesting question to ask, but also having an Aleo credit allows the developers of the blockchain a lot more flexibility. And another question to ask is, would it have been better if Aleo was just a layer two on top of Ethereum? Because that also could have been very possible, right? And that would have made Aleo not have to bootstrap its entire ecosystem, create a new and essentially like made developer onboarding easier and like linked Aleo a lot more to the shared security of Ethereum itself. Um, but yeah, Aleo overall is really great experiment in showing how blockchains can be constructed in a very privacy by default sort of system. Um, a question to ask is whether you want privacy by default or whether you want configurable privacy, which is what we get to next. But I'll just stop you for a question for a second.
No specific question on it, but if I understand Aleo as a whole, is it fair to say it's essentially, doing they're offering AWS services, but they have essentially, divided the computation and the database arm into the blockchain and the ZK cloud.
Yeah, it's not
So
necessarily like AWS, but I guess yeah, like you could say it like that, right? Because the transactions happen off chain on like a cloud type of system,
right,
which you can think of as an AWS, but a private one. And
correct,
and essentially all the transactions are and all the proofs that like all of those transactions happened are stored on the Aleo blockchain.
correct, and blockchains are analogous to databases.
Yeah.
Um,
Hmm.
so okay, and of course everything is on the backbone of ZK proofs. So yeah, I think I
Yeah.
think I I think I understood Aleo.
Cool. Now let's go into Espresso Systems. Now, what Espresso Systems is it's a team of researchers from Stanford's Applied Cryptography Research Group that came together to form this beautiful company. And one of its primary products is this thing called CAPE, which is Configurable Asset Privacy Protocol. So this enables digital assets to have configurable privacy. So users can create, they can create new assets on CAPE, which are privacy enabled, or actually even give existing ERC20 assets privacy features. So what happens is that users lock existing ERC20 tokens within wrappers and they mint them one-to-one within the CAPE system. These assets can be unwrapped back into ERC20 tokens. What obviously this adds is a level of risk of ensuring that the assets locked in the wrappers are safe and not able to be accessed by rogue actors. So that's a risk that the CAPE system introduces. So what happens in CAPE is that users own asset records. So the assets records specify the asset type, owner's address, amount, etc. And the asset type also defines the privacy properties of the asset, right? So you have asset viewing and asset freezing policies. So the asset viewing policies are where the configurable privacy element comes in. So you can, for example, enable address viewing, which goes like authorized users can follow transactions from the asset creator without seeing the value of the transaction. When you have amount viewing enabled, authorized viewers can see the value of the transaction, but not the recipient. And when you have both enabled, you can see both the recipient's address and the amount of the transaction. So you can essentially choose what to make private or not make private. And each transaction itself is a zero knowledge proof within which the transaction details are encrypted, right? So these details that I said, like the amount and the address, they are encrypted. And the only way you can decrypt them is by holding this thing called a viewing key. If you hold the viewing key and turn it into the lock, it then decrypts it then decrypts the details that we were talking about, the address and the amount. And you can distribute viewing keys to these authorized parties. And therefore, they're the only ones who can decrypt them. And what happens is that CAPE also has made some things easier, which is you create transactions via the CAPE wallet. Might add some friction to the user experience because you don't want to have another wallet, but fine, it's for another day. And what you do is you submit these transactions to a relayer rather than directly to CAPE's smart contract on the Ethereum blockchain. Now, what the CAPE smart contract on Ethereum, it maintains the state of the CAPE system, so account balances, etc., all of those things, and it ties CAPE to Ethereum very solidly. So the relayer forwards the transaction data to the CAPE smart contract on Ethereum to be validated, and pays the gas fee to do so, right? This ensures that the Ethereum transaction fee can't be linked to the original user on the blockchain. So that preserves the privacy. Now, obviously, there's a point of centralization here, which is that, is there only one relay that's controlled by Espresso? Is there a way to prove that it's doing its job correctly? If the relayer pays the gas fee every time, is this reflected in the CAPE fee that's paid by the user? So, it's more like from an economic perspective, who's going to be bearing the brunt of changes in gas fees and differences in fees paid? And, is there a way to decentralize this relay and reduce this single point of failure? But that's one of the wrinkles with CAPE. But yeah, I'll stop here for this and if there's any questions.
No, I think we can continue.
Cool. And the last innovation in ZKPs that we're going to talk about today is Lagrange, right? So cross-chain interoperability, so like sending assets from one blockchain to another, it's one of the biggest problems in Web3, right? We've seen that in the number of bridge hacks, and the number of different types of risks that it introduces. So security, operational complexity, so many different types of risks. Now, solving this problem has been one of the most important things that developers and protocols are working on at the moment. And what Lagrange is doing could help that process move along a lot quicker. So what Lagrange does is it develops these thing called state proofs. So these state proofs attest to the state of a chain at a specific point in time. So let's say that it's Monday, 17th April, 10 p.m. And at 10 p.m., I can attest that these were the account balances, addresses. Essentially, this is the state of the blockchain at this one point in time. And it can do this for a number of different types of blockchains, right? So these allow users to verify the integrity and accuracy of a specific piece of information or a transaction on the blockchain without actually having to download the entire data of that blockchain, right? So that, it speeds up things quite a lot. It also simplifies transactions and makes them more secure. So let's put this into a practical example, right? So consider a situation where a user wants to use their ID, right? So they've been verified on Solana, and they want to deposit to a permission vault on Dopex, which we've spoken about before, on Dopex on Arbitrum, right? On the Arbitrum blockchain. So in today's world, what they would have to do is that they would have to submit a transaction to Solana, to a smart contract on Solana. Now the transaction emits an event, right? What happens is that there's an intermediary messaging layer, right? There's a messaging protocol, so something like a layer 0. So that messaging protocol listens for these events and goes like, okay, I've heard this event that I wanted to hear. This user submitted a transaction on Solana. And it collects a fee from the user and submits a transaction to Arbitrum that contains a timestamp proof of the user's ID on Solana, right? The user then submits a second transaction on Ethereum, on Arbitrum, to deposit assets into Dopex. So what happens is that you have 4 separate transactions that you have to pay fees for. You've got to pay for a Solana transaction. You have to pay for 2 Arbitrum transactions, which is essentially to, the proof of the ID on Solana and to deposit assets into Dopex. And you have to have the 4th one, which is essentially the fee for the messaging protocol. What Lagrange allows for is that the user can attach a Lagrange state proof to a single transaction on Arbitrum and pay only one set of fees. So what I can do is I can just deposit into that vault on Dopex, and it's got that state proof attached to that transaction, which essentially shows that this is my ID on Solana. It's valid as of this point in time. And therefore, this can increase speed, it can increase scalability, it can increase flexibility, improve the user experience, all of that stuff. Because all the user has to do is submit only one transaction on Ethereum. On Arbitrum. So yeah, multiple state proofs can be combined into one big proof, right? So this proof can, it can do things like verify users' collateral across chains, increase capital efficiency, eliminates the need for trust between Arbitrum, Solana, and the user. The user doesn't need to re-authenticate themselves across chains, lots of things like that. So essentially, what Lagrange is doing is bringing a lot of flexibility to the entire blockchain ecosystem. And it just makes things a lot easier for developers, for users, for essentially everyone. So yeah, Lagrange is also doing pretty cool things with zero knowledge proofs. And yeah, I think I'll stop here.
Yeah, no, this one is super interesting. So essentially, would it be fair to say that Lagrange itself is a cross-chain, messaging protocol? Because all it does, if you take the example that you just went through, all it's doing is just, telling
But it's not
Dopex.
actually doing the messaging. That's the thing. It's only providing the proof of like it's only providing proof of something. It's not passing messages between any two parties. What it's doing is saying that this is correct, right? Like what has happened at
Yeah,
one point of time is correct.
correct.
It's not actually sending that correct message to someone else. What the developer does is it uses a Lagrange state proof and puts it on the transaction to go like, okay, Lagrange's state proof has verified that this
Well,
person's
okay, okay,
position on chain
okay,
is,
okay.
yeah,
So the output of Lagrange can be used, as a alternative to actually sending value across chain,
messages, exactly.
messages across
Not
chain,
even
and
value, but messages. Yeah,
no, I'm saying it eliminates the need to actually, make the value transfer, because instead
yeah.
of
It
actually
it
transferring tokens,
exactly.
you message saying that you have X amount of tokens on other blockchain, and that lets you avail all the services that you might need on the, the recipient blockchain.
Yeah, exactly.
Interesting. No, I get this, but this is really fascinating.
Cool. Yeah. So I think I think we've gone down the zero knowledge rabbit hole today. It's been a pretty interesting journey. I think that for the sake of everyone's brains, we're gonna stop it here at the moment. But there's a lot more cool stuff being done in the zero knowledge space. Other projects like Supranational and Gonyama, other ones that are very, very complex, and I can't get to the bottom of them because where my understanding stops is to actually decipher the mathematical algorithms. But yeah, there's lots of various applications, and you know, it's uh, it's a fascinating space to keep track of and be involved in.
Yeah, cool. With that, let's wrap things up. So thanks again, everyone, for tuning into this episode of Genesis Block. Looking forward to seeing you on next one.
Cheers, thanks everyone, and have a good one.